Only one banana was damaged in making of this video. In this video, we're going to talk about what happens when a damage is... In this video, we're going to talk about what happens when a banana is damaged. So I did happen to take a hammer and hit the banana peel. So the banana was already peeled, and I took the peel after my kids ate it, and then used the hammer to cause some damage to it. And I wanted to measure what happens over the next hour of that banana. Oftentimes when we get our produce from the store, if it's bagged improperly or that bag is dropped, you start to see a brown spot form in the area of that damage. And so I was interested in understanding, can we track this process over time? Can we use a device like this, a portable near-infrared spectrophotometer, which has the ability to take time-resolved measurements to understand this process? Now, during damage, it's widely known that there's enzymatic breakdown, there's other processes that might accelerate ripening or introduce new bacteria to it during cell rupture and other phenomena like that. So I just wanted to understand, can we see chemical changes? What those exact processes are, this may not be the best device for that, but it can help us to understand what's happening chemically through the lens of a near IR and what we're seeing visually with our eyes in the visible spectrum. So to do that, I want to now process that data. We're going to use TS&E, which is a manifold technique for visualizing that change. Now, what's going to be a little bit different in this video is that instead of choosing set values, I want to demonstrate how we can use the combination of a for loop and something similar to what we've done with grid search to help us understand what are the best parameters for TS&E. Now, if we look at the documentation, we have the number of components and the perplexity. And I want to focus on this perplexity argument here, where this is a value that helps us to tune how much the models weigh local similarity versus the overall similarity. So this is kind of tuning the nearest neighbors approach. How near do neighbors need to be as it attempts to determine similarity between points that are close to each other and how we weigh those points that are farther away. If we look at our data set for this video, this is another comma separated value, and we're going to be measuring our sample every 6 seconds. We're going to just measure for 1 second at a time. And so as we look at our raw data, we're going to measure the sample every minute for an hour. As you can see, our date time is starting at 1:09. Actually ends at 1:09, but it began at 12:09. So we're just monitoring for an hour, and we're just going to scan the device for 1 second per minute. And then from there, we're going to look at the full wavelength spectrum in this near IR device, and then visualize that data using TS&E, like I said before. In this notebook, we're going to begin, as we always do, with importing the standard libraries. Let me set up my environment. We have a couple of our go-to signal processing techniques, and we have a way to further clean up our data set. We're going to drop the unnecessary columns as well as read in our data. The other thing I did was to separate the date time. So I'm going to convert it to date time, but then extract the time and then include a time delta column. The reason for this is that it makes the visualization a little bit simpler. We don't need to consider the fully formatted date time. And I just want to look at the time delta. I want to understand what happens at time 0 versus 60 seconds, 120 seconds, 180 seconds. You could choose to do this a different approach. But as you see, I have the chained methods here. Again, this is why I really enjoy chaining methods. It's really clear as to what's happening as we go from our original data frame to our final data frame, where I'm previewing the first 5 rows of that table. Next, I'm going to use this TS&E from scikit-learn manifold, and I want to explore a number of different perplexity values. As I mentioned before, perplexity can really augment what the data looks like and how much it weighs near neighbors versus more distant neighbors. Thus, understanding which is the most optimal really depends on the context of your overall data set and the visualizations that are produced from these different values. And so we're going to understand that. To do that, we're going to first initialize a base figure, and I'm going to make it fairly large as a 20 by 12. And then I want to loop through a number of perplexity values. In this case, we're going to use enumerate, where I will become the index values. So the first perplexity value at 5 will be 0, 1, 2, 3. And then from there, we're also going to store each of these values in this perplexity variable there. We're next going to initialize TSNE with the looped perplexity values. We're going to set our n iterate to 1000 to give ourselves the best chance of this model converging. And then we're going to fit transform our data frame. We're going to pipe our Savinsky-Golay filter to smooth out the data. And then we're going to create a scores plot. Effectively, what is a scores plot? This is more language tied to PCA. But because we're used to that, I just want to use scores. And then assign our columns to be TSNE1 and TSNE2. We'll make sure the index stays the same. So we want to ensure that these values are the index values. So we're going to assign this as df.index. And then we're going to create our subplots to allow us to visualize the outputs from our perplexity values. When we do this, we will get a number of different outputs. This will take a slight while. And I want to move this over. If you click the top right corner of this figure, we have this way to pop it out into a new window, which will allow us to zoom in a little bit more. When we look at a perplexity of 5, you see we get what looks almost like overfitting, and this is really overfitting to our nearest neighbors. So the more blue is the time towards the beginning of the experiment. This is right after the damage to the banana, right after we've struck it, and then it kind of moves through to darker red. And we can generally see a pattern that's forming, but you could tell perplexity of 5 is probably too small for this data set. It looks a little bit unnatural in the way the points are clustering and a little bit too linear, particularly in this vertical direction. If you go to a perplexity of 10, where we're now considering some of the weight from the more distant neighbors, you see that we have a better looking gradient where we have time 0 on the left. And as we move further to the right and slightly up, we have our later time points. If you can see that there are some changes in the Near IR spectra of this data that's correlated with time, likely correlated with damage. And I was simply measuring this by allowing the probe to sit on the banana peel for the entire hour. And so there should be very little variation due to repositioning and other things like that. If we look at a perplexity of 20, you see that, again, we have a slightly different trend as it's going down and slightly up. But again, I like the fact that it seems more smooth than what we had in the beginning, where we have this significant jump here at all of our sort of time 0 points, early time points. If we look at a higher perplexity of 30, you see that we now continue to see a separation from our early points into our later points, kind of in this zigzag type direction. And if we continue to move on to 40 and 50, we continue to have more weight given to some of the more distant neighbors. I think overall, while this is still a very highly subjective way to visualize, I believe for me, the perplexity value of 20 is the most ideal, as we don't have what looks to be sort of overfit, but we have a nice smooth transition. We do have a gap here. So maybe when I was checking the position of the probe, I didn't sit it down the exact right same position, but this definitely feels smooth. It definitely seems like what we would expect to see with the data. And thus why we were scanning so many different perplexity values, so that we can make sure we avoided something like this, where again, it looks a little bit unnatural in what we would expect the progression to be. We expect relatively linear changes in the data. We expect some noise, but we don't really want to weigh this point so heavily by the next point. And this over here seems like it's a little too big, considering how much these points are to turn this 90 degrees. We expect a probably relatively smooth transition from the early time points with little damage, particularly cell damage, and to the later time points as we see these enzymatic processes change. Now, there are other ways we can visualize this. PCA is a fantastic technique. We can also apply other clustering techniques to help us understand what's going on. But when it comes to how we optimize, using a for loop to look through these perplexities is a great technique. And what I might do is now maybe instead of going all the way up to 50 and down to 5, focus maybe on 15 and 25 to see if there's a more optimal middle point in that range there, like we would do with grid search. And this is just one way to visualize highly complex data, particularly if it's time series data. And if you want to see more like this on this channel, like, comment, subscribe, and I'll see you in the next one. Peace.